So this is part 2 of our lecture on recursion. If you haven't watched the first one yet, you might want to go back and watch that one. I'm going to cover a more advanced recursion problem in this one. As I said in the last problem, basically every problem that you can solve with loops, you can also solve with recursion, but the same is not true in reverse. There are actually certain problems that are only solvable by recursion, and there's a lot of problems that are really well suited for recursion, even if you could solve them with a loop. The problem that we're going to be working on is to generate every possible combination of choices that a player could throw in games of rock, paper, scissors, wherein is just the number of games that are going to be played. So for instance, if we were going to have 3 games, it would say rock, rock, rock. And then there would be one that would be rock, paper, rock. And another one that would be rock, scissors, rock. I'm not going to write them all out right now. But the reason that this is a particularly good problem for recursion is because we are generating almost a tree-like structure of possible choices, where if rock is our first choice, and I've actually got a diagram of this, so we'll jump over to it. So if rock is our first choice, then we have essentially 3 subtrees that can come from that choice being thrown. One where rock is the second choice, one where paper is the second choice, and one where scissors is the second choice. And then from each of those trees, we can even have further subtrees. So if we threw rock the first time and rock the second time, then it's possible we could throw rock the third time, so we'd have to generate a unique combination for that. We could throw paper the third time, we'd have to generate a unique combination for that. And we could throw scissors the third time, so we'd have to generate a unique combination for that. You'll often see recursion problems broken up or diagrammed like this, visualized like this. So anytime you run into a problem that could be broken down into the same problem, where you're solving the same problem, but in smaller and smaller ways. So you start with a big thing, and you break it down into smaller and smaller problems that are solved in the same way. That's a great problem for recursion, and a problem which you'll likely be able to diagram in this tree-like form, sometimes called a decision tree. So let's get into solving a problem. So we have our function rock, paper, scissors. And we know at some point we'll need our base case, where we stop recursing, and we'll need our recursive case. We'll also need an array to hold our results. So I'm going to start with an empty array. And we'll want an array of choices that are just rock, paper, and scissors, just so that we have something to pull from as we recurse down the tree. It'll make more sense in a second why we have these choices kind of hard-coded before we get into it. So to solve this problem, to start out with, I'm going to actually use an inner function that's often called a subroutine. And the subroutine is going to be doing the actual work of recursion. So we'll just call rock, paper, scissors once, but then rock, paper, scissors will call our inner function, which generates our combinations. So that's going to be called recursively. So that's what's going to need our recursive case and our base case. And we know we'll have to call combos down here with some kind of input. And eventually we'll return results. Let me go ahead and say console log rock, paper, scissors. I'm recording this lecture over again because the first time I had the solution completely correct, and I kept calling rock paper scissors and not seeing anything in the console, and because I wasn't console logging, and of course I realized it immediately after I shut off Zoom. All right, so what's our base case and what's our recursive case? Our base case is when either it's going to be when we don't have any more rounds to play. And when we're calling it recursively, we still have rounds and we add new combos. So our recursive function is going to be keeping track of two things: how many rounds have been played, and what combinations have we generated so far. So I think that I will give this parameters, rounds for what rounds we've played so far, and then played to keep track of our combinations. I'm giving it these parameters because when we call it recursively, I'll be able to alter the inputs to change what's happening inside of each recursive call. So let's look at our base case first. We could count up to n. I'm going to count down to 0 instead. So I'm going to say when rounds equals 0, then we'll return. I don't know what we'll return yet. In terms of our recursive case, we know that looking back at our diagram, each recursive call down, so kind of each level down, we need to be adding all three choices. So I'm going to construct a for loop. And while I is less than choices.length, I'm going to iterate over choices and add each choice. So I'll say current equals choices I. And then what I'm going to do is call my recursive function again with rounds -1 and then I want played with the new choice in there. Let's see. I could push current into there and then just pass played, I think, to be a little bit more succinct. And also, again, I like to, in order to control my recursion, I like to change my input each time so that recursion is doing the work rather than altering what happens inside of my recursive function and then passing that in. So I'm just going to concat current onto played each time we pass it in. What's going to happen is, for instance, when we first call rock, paper, scissors and then call combos, it's going to start out with I equals 0. So it'll choose rock. So played is going to then just be an array with rock inside of it. And rounds will be -1. And then it's going to recurse down one level. And when it goes down a level, inside of that level, it's going to end up iterating over all of the choices. And what played is equal to, so we have an array that's just rock. And each of those is going to be concatenated onto played. Okay. Actually, now that I'm thinking about it, if you recall, our output was going to look like this. So let's see. We could say played plus equals current because we're actually making a string, not an array. I don't know if that'll work. I might actually still use the concat method. I'm going to test this out though. So at the end, when we get to the bottom and we've constructed one of these combinations, we'll want to push that combination to results. So we need to call this with an initial input. We can give, we can pass in as rounds so that we have whatever in is passed in as our initial rounds. And then if we're concatenating onto played, we'll need an empty string to start with. So I think this might work. Let's test it out. Oh, one thing we might want is to have a space. So this way we can add a space in our output. There's something that's incorrect about this where we're generating combinations that are more than 3. Oh yes, I think that maybe by using plus equals, I was reassigning played so that when it returned up a level, played would still have that current attached to it, even though it was going down a different recursive path. Let's try it out. Okay, this looks more correct. Yeah. So this has given us the output that we want. Again, what was happening before is that when I had it set to plus equals current, I was reassigning what played was equal to in the scope of that particular level of the recursive stack. And so, for instance, if we called combos recursively with rock, then in the next iteration of the for loop, rock was still attached to this instance of played. And so rock was on there and it would attach scissors too, and then recursively call down. And so we were getting down to certain calls where we had all 3 choices for one game, and then we would have additional choices for the next game. So instead, we use concat because this won't change played. It just creates a copy that we pass down. And that is recursion.